Okay, in this problem we need to set up whatever integrals might be needed to find the volume of the solid form by rotating the region bound by these two curves, y equals negative 2x squared plus 8x plus 1 and y equals 2x plus 1 about the line y equals negative 1. So we're finding a volume of revolution. So the first thing we need to do, of course, is get a better idea of what this region looks like. So to that end, we'll graph this quadratic function first. And not surprisingly, the graph is a parabola. Of course, we can find the vertex of the parabola fairly quickly by completing the square, as we show here. Of course, we need to factor this negative 2 out, and then ask ourselves what is the missing third term here that would make this a perfect binomial square. Of course, that's going to be half of negative 4 squared, which is 4. The real effect of inserting that 4, of course, is to subtract an 8, this product here, and so we add an 8 on the outside to compensate. Now we can rewrite this as our perfect binomial square, namely x minus 2 squared. This collects together to give us 9, and this reveals our vertex, which is then at 2, 9. And so we've plotted that point. Also, of course, the y-intercept is always easy to find. Simply plug in x equals 0. Those terms there vanish, leaving y equals 1. So we've marked that point as well. So that's one of the curves that defines this region. We need to graph this other one as well, y equals 2x plus 1. Of course, that is just a line, which is quickly graphed upon noticing that it also has a y-intercept of 1 and a slope of 2, a positive slope of 2. So we're rising up here to some intersection point, which we don't yet know. So this yellow region here is the region described in the problem. And that's what I need to rotate about the line y equals negative 1. Now I do want to completely describe this region. I want to find all of the interesting points, especially points where x's and y's obtain the maximum or minimum values they might have for this region. So I do want to actually get my hands on this point of intersection. Of course, that intersection happens where these two functions, negative 2x squared plus 8x plus 1 and 2x plus 1, agree in height. And so we simply set the y coordinates equal to one another, and we can solve that. And of course, that's just a quadratic equation, so that shouldn't be too terribly difficult to solve. Pulling everything here to the right-hand side and getting 0 on the other side, we can see that x has got to be either 0 or 3. Okay, and this is not surprising because one of the intersections of these two curves happens over here on the y-axis. That would be when x equals 0, and the other one occurs for some positive value of x, and presumably that's going to be this x equals 3. We want to find the y values associated with both of these, of course. And to that end, we can find these y values simply by plugging in these x values into either this function or this one. Of course, this one is the easier one to deal with, so 2 times 0 plus 1, that's where our y equals 1 comes from, and 2 times 3 plus 1, that would be where our y equals 7 comes from. And so now 3, 7 must be this point of intersection. Okay, and so we'll label that accordingly. Okay, so now remember, we are taking this region and rotating it about the line y equals negative 1. Okay, so let's go ahead and draw in that axis of rotation. Okay, so there we have that line. Now, we could proceed a couple different ways here. One, of course, would be to get kind of a holistic view of what this rotated region looks like. Of course, if we take this little tiny arc here and spin it around this y equals negative 1 line, we're going to produce a region not dissimilar from something that looks like this. Okay, you can see this tiny region here corresponds exactly to this yellow region here, and we're just spinning it around to create kind of a bowl shape that's up on its side. But this type of picture can be kind of tricky to draw, and even more tricky to actually deal with them in a meaningful way. So what we're going to do is we're going to try to make this a simpler problem. We're going to take this area, which has some curved boundaries here, and we're going to slice it up into rectangles and see what the individual rectangles are doing when they are rotated about this axis of rotation as opposed to the entire curve. So let's go ahead and cut this region up into rectangles. Okay, something like this. Now notice I do have a choice here. I could cut this up into rectangles vertically, or I could have cut this up into rectangles horizontally. And depending on how you do that, when we spin these individual rectangles around the line y equals -1, we're going to produce different little pieces of this overall orange volume. In one case, we're going to get pieces that look like washers, and in another case, we'll get pieces that look like cylindrical shells. Okay, so there is an important choice to be made here when you're deciding should these rectangles be vertical or should they be horizontal. But here, let's start with these rectangles being vertical. And really, the more important thing is not so much that it's vertical, but that it's perpendicular to our axis of rotation. Okay? So when the rectangles you choose end up perpendicular to our axis of rotation, look what happens. Let's look at one rectangle in particular. Say this red one right here. Now if I take that red rectangle and spin it around this axis of rotation, look what we get. You see here we get a washer. Okay? Indeed, every single one of these rectangles, when spun around this axis of rotation, is going to produce its own washer. And every one of those washers contributes some sort of volume to the whole volume indicated down here. So if I want to find this volume here, I simply need to add up all of the washer volumes I could get for each one of these rectangles in this area. Now, if I'm going to be adding up washer volumes, I need to have an idea of what a washer volume looks like. So let's remind ourselves of how we might calculate the volume of a washer solid. Laying this thing down on its side, we can see that it's going to have some sort of thickness or height here, as indicated by h. We have an outer radius for the outer edge, which is of course is a circle, and we have an inner radius for this inner circle. Now one way we could get our hands on the volume is to treat this as a difference of two cylindrical volumes. You have this outer cylinder, very short, very squatty cylinder, minus this space on the inside here, minus this volume on the inside, which itself is a cylindrical volume. Recalling that the volume of a cylinder is given by pi times the radius squared times the height, this outer cylinder with this filled in would be pi times big R squared h, and the inner cylinder, which we have removed, would be pi times little r squared times h, and so simply subtracting those and maybe pulling out the common pi and the common h, we have this expression here. Okay, let's slide this up a little bit so we've got some more room to work. There, that should be good. Okay, and let's also remind ourselves of the process by which we found areas bound by curves. So we might use that to inform how we can find volumes, such as this one. So recalling, when we had an area that we wanted to find that was bound by curves, we sliced up the region into rectangles. Maybe those rectangles were vertical, maybe those rectangles were horizontal, but I wanted to add up my approximations for each of these little rectangular strips, and assuming they were actually rectangles, we found a length and a width for each, and of course then added those products, right? That's the area of a rectangle, length times width. Of course we could do better than length times width, because the length of this red rectangle here would be given by the height of the function, right? The y value, the f of x value. And the width of this rectangle here would be a tiny, tiny change or difference in x. And the same thing goes over here. We could express the length of this rectangle as some sort of function of y, and the thickness of that rectangle, which is very, very small, as some tiny, tiny difference or change in y. Then in the limit, as we let these rectangles become very, very thin, and as such they did a very good job of approximating, when added together, the areas here shown in yellow. In the limit, this sum of product that either looked like some function times a change in x or some function times a change in y, those became definite integrals, right? And the delta x essentially changed into a tiny, tiny dx, and the change in y over here, the delta y, changed into a little tiny dy here. And again, we have the integral sign, the Latin s, replacing sigma or the Greek s, both of which suggest, of course, some sort of summing behavior. Well, we want to do the exact same thing here with washer volumes to find our overall volume. We want to add up all of the individual washer volumes. And just like I replaced rectangular areas with length times width, I can replace washer volumes now with this formula for the volume of a washer, namely pi times big R squared minus little r squared, that whole quantity times h. And then the hope would be, just like we did down here, to convert this sum into a definite integral that has this same form. Except for, notice I've replaced h with d something. Maybe that's a dx, maybe that's a dy. Look, this thing here corresponds to h. What is h? H is this little tiny thickness here of my washer, which up here would be that little measurement right there, right? Notice, that is the width of this red rectangle as well. And the width of this little red rectangle, that's a little tiny horizontal measurement, right? So a little tiny horizontal segment. Is the length of a horizontal segment the difference of x coordinates or the difference of y coordinates? Well, that would be the difference of x coordinates. This is a little tiny difference in x. And so our h, again, being this little tiny difference of x values, a little tiny change in x, that's going to correspond in our integral, our definite integral that we're setting up to be a dx. Okay, so I'm going to make that replacement. But I've got other replacements to make as well. I've got to replace out this big R and this little r. Now notice we have this replacement here marked, but let's kind of figure out where that came from. What is big R? Going back to our picture here, it's the distance from the center, that would be of course the axis of rotation, to the outer edge. Okay, so I find the center of my washer, again that's sitting on the axis of rotation, and I go out to my outer edge. So it's this distance from this purple dot to this purple dot. Again, notice this is a vertical distance. Okay, a little vertical segment here that we're finding the length of. So we find the length of vertical segments by taking a difference of what? X coordinates or y coordinates? Well, of course, if we want the length of a vertical segment, we need to subtract the y coordinates there, the difference of the heights. So I need the y coordinate here, the height at this point, minus the y coordinate here. And notice we have to subtract them in that order, otherwise our length doesn't make any sense. If we subtracted this y coordinate from this y coordinate, we would get some sort of negative value. So we do it in reverse. We always take top minus bottom so that our result must be positive. Okay, so what is the y coordinate here and what is the y coordinate here? And what are they? And this is very, very important in terms of this variable. Okay, our identification of h as a change in x and subsequent identification of the variable of integration being x requires that all of these things here be expressed in terms of that variable. Okay, so in this case they have to be in terms of x. Right? Had we picked dy here, all of these things would have to be in terms of y. So not only do I want to find r as a difference of y coordinates here, but I need to know what that difference is in terms of x's. So that means I need to know what is y up here in terms of x, what is y here in terms of x. Well, fortunately, we know what y here is in terms of x. If we take this rectangle, as indicated by this little red letter here, if we take that rectangle as having an x-coordinate of simply x, then this would be the height of the parabola at that x-coordinate. So this should be f of x, which is given by this. Okay? That right there, negative 2x squared plus 8x plus 1, is the y-coordinate of this point in terms of x. And the y-coordinate down here, well, that's always negative 1. You can think of that as in terms of x or in terms of y, depending on what you need. Okay? So big R, which is the difference of these two, should be negative 2x squared plus 8x plus 1. That's the y-coordinate of the top, minus the y-coordinate of the bottom, which is negative 1. And then, of course, we simplify that. We can find little r in a very similar way. Remember, little r is the distance between the center, where the axis of rotation would be, and this inner edge. And so on our picture here, that would be from the center to this inner edge, from this point here at height y equals negative 1 to this point here on this line. Okay? Again, this distance is a vertical distance, and as such must be a difference of not x coordinates, but again of y coordinates. So I need the y coordinate here minus the y coordinate here. Again, top minus bottom all the time, so that we get a positive result. The y coordinate here, though, I need to express in terms of x's. Fortunately, I have that. Y equals 2x plus 1 at x. And the y coordinate here again is negative 1. And so r, little r, is 2x plus 1 minus negative 1, which again I simplify. Now we can take all of this information, big R, little r, noting that we have a dx here, and create a corresponding definite integral. Okay, now notice it's not a definite integral yet because I haven't dealt with the limits of integration, but this would be the form that we're after. Now, speaking of limits of integration, what are those here? Well, remember, those values should indicate the range of x values, again, appealing to whatever this variable of integration is. If this was a dy, I'd ask myself the question, well, what y values are appropriate here? But here it's an x. So what x values give me the range over which I will actually have washers produced? What's the smallest x value that's going to produce one of these washers? Well, the smallest, the leftmost here, that I need to go in terms of my region would be right here. That would be at x equals 0. And what's the rightmost point? Well, I'll get a rectangle there, and there, and there, and there, all the way up to x equals 3, and nothing past that. So it looks like the interval over which I'm producing these rectangles, and hence producing the washers, goes from 0 to 3. And so that's what I'm going to mark as my limits of integration. Okay? Guess what? We just set up an integral that will give us this volume of revolution that we seek. Okay? That's one way to do it. But remember, we made a choice early on with regard to how this region was cut up. We cut things up vertically so that our rectangles were perpendicular to our axis of rotation, and that produced washers. But what if we cut up our region differently? What if we chose horizontal rectangles which were then parallel to our axis of rotation? Like so. Well, let's see what would happen when one of these rectangles is rotated about this axis of rotation. So let's pick one. maybe this red one. And if you're on the ball, you'll notice that actually this red rectangle here is going to behave differently than maybe a rectangle chosen from up here, but we'll address that point in a few minutes. Okay, let's take this rectangle and spin it around the line y equals -1. Notice the shape here that was created, the volume created here, is different. It is not a washer shape. This is more like a cylindrical shell. Just like we could express the volume here of the overall solid of evolution as the sum of a bunch of washer volumes, we can also consider all of the cylindrical shells that would be produced by these various rectangles and add up their volumes to arrive at that same overall volume. Of course, that begs the question, just like it did for washer volumes, well, what is the volume contributed by a single cylindrical shell? So let's take a look at that a little bit closer. Okay, so here we have a shell turned on its side again, so we can easily identify the different pieces. We have a height here, much more substantial than we had with the washers. We have a radius from the axis of rotation here to the outer edge, and then we also have a little tiny thickness or width of the shell. And with a little bit of geometry, and noting that this W here is typically going to be very, very small, the volume contributed by this one cylindrical shell should be given by 2 pi RH times W. And again, just like before, like we were motivated by adding up rectangular areas of the form length times width, and then turning those sums, or that sum, into a definite integral that bears a very similar form, we want to do the same thing here by adding up these cylindrical shell volumes. So if we add up those cylindrical shell volumes to approximate V, this total volume here, then we're adding up things that take this form, right? Our 2 pi RH times W. And that hopefully will lead us to some sort of integral of the same form. Maybe something like this. And again, notice we've got the integral of the 2 pi RH, that part there, and then I've replaced W with d something. Maybe that's a dx, maybe that's a dy again. What is it here? Well, again, notice W is this little tiny thickness. If I find that same thickness up here, notice it's this little tiny height here, this little tiny length of this vertical segment. That being a vertical segment, its length is going to be a difference of what? Well, a difference of y coordinates. Okay, and so this width is a change in y. It's a delta y, and so this is going to determine our variable of integration in the integral. That's going to become dy, and that's very, very important, and you always want to go after this guy first, because remember, all of these other things here will need to be expressed in terms of that variable. So I will need to find r, and I will need to find h in terms of y, so that I can actually do the integration. Okay, well, what about r? What is that in terms of y? And of course we have our answer here, but let's see where it came from. Remember, r is the distance from the center, where the axis of rotation is, to the outer edge. In our picture up here, there's the center, there's our axis of rotation. Our outer edge would be here, where our red rectangle was chosen to be, and so we're looking at the difference in height here between these two purple points, the length of this vertical segment between these two purple points. And so we find that, of course, by taking a difference of what? X or y coordinates. Well, again, this is a vertical distance, so I'm going to take a difference of y coordinates. So I need the y coordinate here minus the y coordinate here. Now, these need to be in terms of y. Okay? Okay, so I need the y-coordinate here in terms of y minus the y-coordinate here in terms of y. What's the y-coordinate here, sitting on my red rectangle right there? Notice the trick we pulled down here, right? For a vertical rectangle, we assume its position is at x. For this horizontal rectangle, we assume its position is y. This guy right here has a y-coordinate of simply y. And the y-coordinate down here, again, as we said before, is -1. Whether you think of that in terms of x or in terms of y doesn't really make a difference. And so we're looking at y minus -1. Y minus -1. Then, of course, we simplify it. H is dealt with similarly. What is h? H is this measurement here, which, translating it up here, would be the length of our rectangle. Okay, now, this rectangle, is it horizontal or vertical? Well, it's horizontal. So to find a horizontal length, do I find the difference of the x-coordinates at the endpoints or the difference of the y-coordinates? Well, again, being horizontal, we're after now the difference of x-coordinates. So I need the x-coordinate here minus the x-coordinate here. And I need those two x-coordinates in terms of this variable of integration, in terms of y. I need x in terms of y here, I need x in terms of y here. How do we find x in terms of y here? Look, we've got y equals 2x plus 1. Couldn't we simply solve that for x to find x in terms of y? Okay, so y over 2 minus 1/2, that's the x-coordinate in terms of y. Okay, well, what about this one? What is the x-coordinate here in terms of y so that I can subtract these guys? Well, this point is on the parabola. Okay, and so I need to do the same sort of thing to this as we did to the line. I need to solve for x. Let's slide this down just a little bit so we got a little more room to reference something here. There we go. Okay. Now we can solve for x in terms of y in this expression fairly quickly, especially if we appeal to our earlier work where we completed the square. Solving for x here is fairly straightforward. We simply take the 9 over, divide by the -2. Maybe we multiply top and bottom there by -1 so the signs look a little bit nicer. And take a square root, positive or negative, and then finally move the 2 over to the other side to get x is 2 plus or minus the square root of 9 minus y over 2. Okay, we could have done the same thing by applying the quadratic formula here to solve for x as well. Just remember that you need a 0 on one side when you're using the quadratic formula, so you would have had to take the y over here, and that actually gets integrated into part of your c if you do that. Okay, but completing the square makes this pretty quick. Now, what were we trying to do? We were trying to find h. H was this measurement here, so I needed the x-coordinate of this point, which I have, minus the x-coordinate of this point, which I now have. Well, actually I have two things here, don't I? Which one is this point? Is it the 2 plus something or the 2 minus something? Well, notice where 2 is. 2 is where your vertex is at. This point is to the left of the vertex. So this must be the 2 minus the square root of the fraction 9 minus y over 2. And so, down here, h is equal to y over 2 minus 1/2, that was the x-coordinate of that point, minus this quantity here, 2 minus the square root of stuff, which was the x-coordinate of that point. Okay, and then again we clean things up, get common denominators, and so forth. Okay, so we're almost ready to start plugging all this stuff back into here and getting a definite integral to represent the limiting value of such a sum as described up here. Okay, but looking ahead, if I'm going to get a definite integral here, it's going to cover which values of y? Well, the smallest y value that produces one of these red rectangles would be a 1. What's the largest? Well, you have a rectangle here and here and here and here, all the way up to a y value of 9. But notice, and I think we noticed this earlier and just kind of pushed it off to later, the rectangles here are different from the rectangles here in that their lengths are calculated differently. Rectangles down here, you're looking at an x-coordinate of this point minus an x-coordinate of this point. This point is on a line, and so its x-coordinate is given by this. And this point's on the parabola, and so its x-coordinate is given by this. But if you go up higher, for example, this red rectangle, up here, okay, notice the x-coordinate of the right side is on the parabola. I can't use this now. The x-coordinate of this point on the left side, of course, is very similar to the one we had before, but the overall length will change. And look, if y is greater than 7, so we're above this point of intersection, that's when we're talking about this problem occurring, right? So if y is greater than 7, our h is going to change. The x-coordinate of this point being on this parabola is also of this form. Except for if we're on the right-hand side, so we're to the right of this x equals 2, we must be using the 2 plus this square root. And so when we try to find h here, we have a 2 plus this square root. That's the x-coordinate of this guy, minus 2 minus this square root. That's the x-coordinate of this guy. Okay, and then that actually cleans up quite nicely there. The 2's cancel, and you get twice the square root. Okay, so now we are ready to plug this information into this integral form, noting that we really have to consider two different integrals here. One that is going to be valid when y is ranging from 1 up to 7, and the other, right, this case, which is valid from y equals 7 up through 9. Okay, so let's scroll this up a little bit so we can see what's going on here. Okay, so one integral is valid for 1 through 7 in terms of the y values, and there we're using all of this information. Okay, dy, of course, y plus 1 for our radius. Don't forget your 2 pi over here, and then in brackets we have our h value. And then for the rest of it, the top part of that yellow region, from y equals 7 up to y equals 9, same starting point here, 2 pi times y plus 1, but what we have for h is now different. What we have for h is now this expression here. Okay? And so that provides yet another way, one using cylindrical shells, by which we can find the volume of that solid of revolution. That's it, folks.